Okay, good morning, everybody. Let me just go to the first slide because, like, my presentation will be dedicated to the geocenter motion. So, just to remind you, the geocenter itself is a time-varying translation of the Earth's center of mass related to the origin of the solid Earth figure, which is represented by the finite network of stations. So, we are rather discussing the center of network. And while preparing these slides, I was wondering, why do we care about the geocenter motion itself? And I found like three main reasons. The first of which is like the Earth system understanding itself. So the geocenter time series provide us insight into large-scale mass transfer processes and contribute to understanding the global cycles. The second one is like the GNSS excellence. So like the geocenter estimates itself from the POD-based network shift approach mirrors the processing quality, especially in terms of the solar radiation pressure modeling. And the third thing, I don't know if most essential, is the geodetic excellence. So accurate geocenter estimates are essential for maintaining the interframe consistency, so the linkage between center of mass, center of figure, center network. So to millimeter level reference frame accuracy, to maintain the millimeter reference accuracy, to required for satellite altimetry, LEO POD, and gravity field recovery. So we are almost 10 years after IGS Repro 2, when we as a community, we discussed the outputs of in the context of the geocenter motion as well. And like this plot on the right hand side comes from the younger paper, but the conclusion there then were that, yeah, the geocenter motion delivered by the GNSS, by the ACs, include the expected seasonal variation, but also spurious draconitic signals, particularly in the Z direction, and also that the GNSS annual geocenter motion are in reasonable agreement with SLR for the X and Y directions. But in the Z direction, the annual signals derived from IGS solutions disagreed substantially with SLR estimates, and what is more important, the inter-AC differences were quite substantial. So the number of studies have also emphasized the complex nature of GNSS-based geocenter estimates, so that is not something new. And these are because of the strong correlations with other estimated parameters, particularly solar radiation pressure models. But we now live in the post IGS Repro 3 era, so we have like new data set that was consistently reprocessed, covering also multi-GNSS products, so GPS, GLONASS, and Galileo. And we also put a lot of effort on updating the models, standards, processing strategies, also ensuring long-term homogeneity of the series. And we also observe the fundamental improvements in terms of orbit modeling, which is also essential for geocenter motion recovery. So the goal of that particular study is to explore individual behavior of IGS and geocenter series through the last 30 years, and also investigate how GNSS specific errors evolved, including the orbital artifacts, draconitic effects, and also how like this, as I said, evolved with constellation development, also assessing the consistency across different ACs, and then cross-compare the results with the reference series. I took as a reference the geophysical fluid models, LAGIOS-based SLR solutions, and LEO-based geocenter estimates. Finally, I also wanted to provide the combined GNS-based geocenter product, and I will say a little bit more about that later on. But let me first start with the GNSS dataset, and just to remember at that point, I would like to thank all the ACs for their effort and contributions to the community, because without them, I would have had nothing to do in this study. So I analyzed 10 analysis center contributions, which differ in terms of the constellations that were used. So like either these were GPS only, or GPS Galileo, GPS GLONASS, or all the systems all together. and also differ in terms of the arc length. So either 24 hours or multi-arc solutions were used, and SRP modeling, either like the empirical parameters, because different ACs estimate different sets of empirical orbit parameters, or they use the box wing, on top of which the empirical parameters are also estimated, and the contributions also differ in terms of the station network that were used. All these details are presented in our paper, so you can look there. But also, what I wanted to emphasize here is that do not only the repro-free contribution was analyzed, but also the extension that was delivered by most of the ACs and the operational products up to the middle of 2025. So as I said, we also wanted to combine the different series all together in the one, the weighted product, and for that purpose, we built upon the orbit combination principles we developed for the GFZ the SPOC software. So essentially, we use the various component estimation Fürstner scheme to compute the optimal AC weights to improve the resilience against AC specific artifacts, and also avoid full sinus combination. So, but just to cross compare whether we can work directly on the parameter level and get the same results as for the product delivered by the IGS reference frame committee. And thanks to Paul, I also can analyze the IG3 series in this study. So the flow is as follows. So we have the data availability and quality check, then we select the processing window, then we apply the VC to estimate the weights and compute the weighted average. And I will stop for a while on the selection of the processing window, because that's kind of quite interesting for the combination itself, because like we have to choose the temporal window, which means how far back do we need to use the data to properly estimate the weights. And here we can see the mean weights and their temporal variability, like the top and bottom, as a function of the selected estimation window, ranging from 7 days to 12 months. And yeah, like that's kind of trade-off between the latency of the combination and the availability of this and the stability of the weight estimation. So longer windows yield to more stable variances, but reduce the ability to capture the rapid changes. And like looking at the weights itself and the day-to-day variability, we suggested to use we've chosen to use the 3-month solution as an optimal window, but also a 7-day solution as to find out what's the impact of prioritizing the minimum latency. As a reference series, I took the SLR series provided based on Lagios 1 and 2 only, provided by Hongjuan Yu, and the LEO-based geocenter estimates provided by Professor Kwang, and finally the geophysical models that are from the Global Geophysical Fluid Center based on atmosphere, ocean, terrestrial water storage contributions. So going to the results, this is the variability, this is the metric that shows the standard deviation of X, Y, and Z components in 5-year batches to find how the variability was changing in time. So the GNSS scatter, so all the AC contributions are on the left-hand side. The scatter was quite high before the year 2000, and the variability drops after 2005. So then the window-to-window standard deviation differences become lower than 1 or 2 millimeters, roughly. Also, the scatter is at the level of 3 to 5 millimeters for X and Y, while about 5 to 14 millimeters for the Z geocenter component for different ACs. So we see that the differences there are still substantial. When comparing to the reference series, SLR and GNSS exhibit greater variability than LEO and the model-based geocenter series. And here, the continuation of that analysis is the periodogram of all the series, the periodograms of all the series, and we see that the annual signal is dominant in all the components. But for GNSS, so for all the bottom periodogram series, the Z component is affected by the draconitic errors that will be clearly visible if I zoom in. And the dominant harmonics are the third, fifth, and seventh. And if I and then the interesting thing is the ISA product is the least affected by the draconitic errors. The second thing is that we can see the fortnightly tidal aliases at about 14.76 days, which results from the M2 tidal aliasing through the daily sampling, but these are not visible for neither COD nor JPL series. Finally, the combination. So the top three rows, the combination reduces the magnitude of most of the spurious signals, which is what we intended to see, and comparing all the combinations, so IG3 and our combination, these are highly consistent. In terms of the annual signal, the GNSS annual amplitudes are consistent to a millimeter level for X, Y, and by up to 3 millimeters for Z, with some small exceptions, like and the annual phases are consistent to about 20 degrees, also with some single exceptions. We found no link between processing features and systematic differences in the annual amplitude and phases. And going through the geocenter components, for X, the GNSS amplitudes align with LEO and the model, but the SLR is about 3 times higher. For the Y, GNSS amplitudes are about 2 millimeters higher than the model and 1 millimeter higher than SLR and LEO contributions, while for the Z, GNSS, SLR, and LEO amplitudes are mutually consistent, but about 1.5 millimeter higher than the model. But it was nice to see that for the Z component, all the empirical contributions were quite consistent. Yeah, looking at the correlations, but for the series that are bandpass filtered only to isolate the seasonal signal, both GNSS series, so like our combination and IGS combination, are highly consistent with the almost one correlation. And GNSS also show strong agreement with independent solutions with LEO and SLR, and the Y component is the most consistent, with GNSS correlating at the point of 0.94 with LEO and 0.90 with the model, and 0.88 with SLR. So we can find that GNSS agrees better with LEO than with the SLR in all components. Also, the correlations of all the empirical series, so GNSS, SLR, and LEO, with the model range from 0.7 to 0.9074, which is an excellent agreement. Finally, we wanted to find out if we can capture the same variability of the annual signal in the series, and did the analysis of the sliding window annual signal fit, where the model showed the lowest annual amplitude variability, while the annual amplitudes in GNSS, LEO, SLR, these are these thick lines, are more dependent on the processing than expose the response to the geophysical phenomena. And if we could take a look at the correlation matrix at the bottom, we see that GNSS solutions agree better with each other than with any other external models, which is notable in Y, but also for X and Z. And the final analysis is that we wanted to look for the explanation in the change of the annual signal in the general change of other draconitic signals. And here are the matrices for the annual and the third, fourth, fifth, sixth, and seventh draconitic, but we found actually no correlation between the increase of the draconitic and the annual signal amplitude. So this is still something that need to be further investigated, because some unique variability of the draconitic signal magnitude in time was rather identified than the common signals. So that's all, and because I'm out of time, I only say that we provided all these analysis in the paper that we published some time ago, and I'm happy to see that the GNSS solutions show strong agreement with the independent data sets. at the seasonal time scale, which confirms the geophysical origin, but we are still affected by the GNSS related artifacts, which need to be better understood. Thank you. And if you want to use the GeoCenter series we developed, I encourage you to look at the data set at Zenodo we shared. Thank you.